pretty images to show you, but it'll be all squiggly lines today. And here's some of the members of the Crater team that I'm working most closely with, especially Tim Stubbs. So I'll be talking about how cosmic rays and solar energetic particles charge the lunar regolith. So there's a pretty much uncited paper that was published in Science a few decades ago by Campins and Crater, and they experimented with how energetic particles, especially electrons, will deep dielectrically charge sulfur. They were trying to simulate what Io might experience in Jupiter's radiation belt. And here's a schematic over here of what they were doing is they were putting a chunk of sulfur right here. This is the upper surface of the layer of sulfur that they had. And they irradiated it with electrons. And the electrons would penetrate down into the subsurface. And once the electric field from the electrons built up, they would actually have dielectric breakdown. So regions of the dielectric or the insulator would convert from a solid to a plasma, and you get these discharge channels. And where the channels met the surface, you get outgassing. So you can have plasma creation, melting, blowing, mechanical changes. Pretty much you name it, you get it inside there. So my question is, can this happen at the moon? Because I like cosmic rays, so I like seeing what they can do. So what is dielectric breakdown exactly? And there's about 50 years worth of spacecraft observations of spacecraft charging, also dielectric breakdown. So there's this amazing body of literature to draw from, where they've kind of hammered out a bunch of even just rules of thumbs. So this is actually one of the rules of thumb. So what happens is the electric field in the dielectric or the insulator, I'll use those terms interchangeably, the electric field becomes so great that any free electron in the insulator can gain enough energy in one mean free path to actually be able to ionize another atom. When that happens, then you get 2 electrons, and then they gain enough energy to ionize 4 more atoms, and then you get exponential growth. That's the avalanche theory of dielectric breakdown. So the field you need is on the order of about 10 to the 7 volts per meter, although some experiments, lab experiments, show that in a vacuum you can even have electric fields as low as 10 to the 6 volts per meter and still get dielectric breakdown. And that's just because these are overall macroscopic electric fields, and depending on the geometry within the dielectric, you can actually have localized magnetic fields which are much greater than the overall electric field. So the fluence of charged particles that you need in order to get these electric fields is about 10 to the 10 to 10 to the 11th charged particles per squared centimeter. That's another good rule of thumb. And so in this talk, I'm going to be ignoring all other current sources. I know there's photoionization currents. We've got the solar wind currents. I'm going to be ignoring them. And part of that depends on what I'm choosing to study on the moon. And then the dielectric constant that I'm using for the regolith is about 2. So that's from that paper you see there. So in addition to the dielectric constant, we also need to know the conductivity, and that can constrain the problem a little bit. So what I've got plotted here is temperature is on the x-axis, going from absolute 0, where there's nothing down there, all the way up to about the maximum temperature we see on the moon. And then T-min is the lowest temperature that has ever been observed on the moon, so around 30 Kelvin. And then average polar temperature is around 100 Kelvin, equatorial temperature is around 200. And then on the y-axis, we've got electrical conductivity. And so this curve right here is a Apollo 16 rock. And then we've got the regolith, which is what I'm interested in. Here's the functional form. So it's the conductivity is exponentially dependent on the temperature. And so I'm going to be focusing on permanently shadowed regions. That gets rid of some of the extraneous currents. Well, to me, they're extraneous for this study. So I can just deal with what goes on when we have these energetic particles charging the subsurface, charging the regolith. So I'm going to be looking at conductivities of about 10 to the minus 17th mho per meter. I know mho is a little bit outdated, but I like it. That gives a charging/discharging time scale of about 20 days. So if you remember back to the days when you were studying RC currents or RC circuits, that's where that time scale comes from. I had to review all this stuff. I'd forgotten it. So what happens? This is just a really cartoony description of what happens. We have a current of energetic charged particles. In this case, they're probably galactic cosmic rays, so mostly protons, penetrating down into the lunar regolith. Galactic cosmic rays are very energetic, so they can go down a 10 meters down into the regolith. 10 meters is about the cutoff. And they form this charged region. There's an electric field above and an electric field below. And so some of you might have seen my talk at the LPSC. And so this is the way I was thinking about it. Just a simple single layer charging model. And the single layer model has charge dissipation. So you've got a buildup of charge that does have to dissipate over time. And so I had assumed symmetric dissipation. So it dissipates in both directions, but then I didn't really care where that charge went. So what you see is, in the schematic again, you actually get charge separation in two directions. You have a region of charge moving towards the surface and another moving down. And I know the protons aren't actually charging. It's just how the bulk charge flows. You still have an electric field above and below the surface, above and below the charged region. But now you actually have two layers and a region where there's no electric field in the middle. So we need a double charge layer model to actually be able to describe the situation more accurately. And a double charge layer model also has the benefit that you can have different charge species in there, which is pretty nice. So now I can look at solar energetic particles, which have electrons and protons. And so in this model, we've got non-overlapping proton layer, so it's the deeper one, and then an electron layer. And in the case that I'm showing here, maybe there was a solar energetic particle event. We've got electrons deposited near the surface, protons further down. And if they appeared in equal fluences, then we'd have no electric field above, no electric field in the interior, but we would have a strong electric field in between. And then as time goes on, that charging would eventually dissipate. So here's first results from this model. So what we've got is times on the x-axis. The electric field magnitude is on the y-axis. And just to give you a sense for the time scale, we've got an hour labeled day, tau, which is that charging time scale on the order of 20 days, a lunation, a year, it keeps on going. And there's three different electric fields here. So the blue curve is back here, blue solid curve. That's the surface electric field. So that's the electric field above the charging layer. The interior field is the one below. That's the dash green. And if you can't tell the difference between blue and green, it's okay because they always lie on the same curve through the whole talk. So it's okay. You might have trouble if you have trouble distinguishing between red and green. But this is the red curve right here. And that's the electric field within the gap. So what I plot in here is just a proton charge layer. So galactic cosmic rays come in with a flux of about 4 particles or 4 protons per square centimeter per second. And so that's what we've added in this model. And that forms a charge layer, which gradually dissipates over time in the way that I showed you in the cartoon model. So when it reaches equilibrium, you see the electric field in the gap actually does go to 0. Whereas the electric field above and below this charging region actually increase and then eventually reach equilibrium, right around 600 volts per meter. And this, again, is for permanently shadowed regions where the conductivity is really low. So we have nice long charging time scales. So 600 volts per meter, that's actually pretty high. Okay. Galactic cosmic rays are interesting because they penetrate so deeply into the surface. But solar energetic particles, even though they only penetrate down to maybe a millimeter, so a few microns down to a millimeter within the regolith, SEPs come in much greater fluxes than galactic cosmic rays. So I'm showing here the Halloween storms, and we've got about a month's worth of data from 2003. The flux is on the y-axis. And blue is the electron data from ACE, and then the red are the protons from ACE as well. And so you can see that the fluxes are getting up to around October 30th, around 10 to the 6 particles per square centimeter per second. And that happens over the order of about a day. So now you're getting fluences of around 10 to the 10, 10 to the 11th particles per centimeter squared, which, as I said, from spacecraft charging rules of thumb, indicate that you probably get dielectric breakdown. So we plug this time series into the model. And again, the curves are the same thing. Everything starts charging up, and you can see when there's a lot of electrons, you start getting a lot of charging, a lot of protons, and a lot of electrons, you get more charging, and then it slowly starts to decay. The surface and the interior fields are not as strong as the gap fields because now we've got both electrons and protons. So they tend to cancel the fields out above and below the charging layer. So the strongest field is actually between the protons and the electrons. And you can see that the maximum electric field in the gap is right there. It's about 10 to the 7th volts per meter, which is pretty exciting because that's right at the threshold for dielectric breakdown. And keep in mind, it's not a hard threshold, bam, you hit it, and boom, you get dielectric breakdown. It's actually a pretty broad region. I looked at one other event, the Steel Day event in July of 2000, and this actually had even higher fluences, a higher fluence than the Halloween storms did. And here you see that the maximum electric field was over 10 to the 7th volts per meter. So, just in quick conclusion, in permanently shadowed regions, it looks like galactic cosmic rays create electric fields on the order of about 1,000 volts per meter. But what's really exciting is that strong solar energetic particle events, so I think in the past solar cycle there were maybe fewer than 10, but more than 5 events like this, do seem to be able to cause dielectric breakdown in permanently shadowed regions. And so if you go back to this figure again from Kempens and Kreider, you can see that physically what's going on when the dielectric breaks down is really interesting. You get a lot of changes. So what I want you to take away from this is that deep dielectric charging could actually contribute quite a bit to space weathering. So that's going to be some of the future work.
Could this be one of the reasons why the lunar dust stuck to all the clothing and everything else on the Apollo astronauts and was just created quite a problem for them?
Boy, I don't know, because they landed in more of the equatorial regions, so you have a lot of other currents involved. Here I'm trying to just isolate what's due to purely cosmic ray and SUP events. So I think in that case, I'm not really sure.
Very interesting talk. What happens, 2 questions. What happens when an astronaut does a core sample in these charged conditions?
That's a good question. I'm not really sure. I haven't even thought
Second question, is there any opportunity to get energy out of these fields?
Yeah, that's a good question too. I'm going to guess no, because it's over such a small depth. So you're down to about a millimeter. It's very small. So if you could have some way of creating a huge collector array to do that, then maybe. That's also true, yeah.
Actually, I have a question. You were talking about how this could affect space weathering, but as Matt Siegler was showing yesterday, we have to play around with the conductivity or the density of the materials in the permanently shadowed regions to come up with the temperatures we see with Diviner. Is this a potential mechanism for making things more porous than other places on the moon?
It could be, but again, it's still limited to that